Hi, good afternoon, everyone. Sorry for the late start. We had a bit of a technical issue, but I think we have it resolved now. Today we have Burns Foster from CARIS. He's a product manager for CARIS Hips and Sips. He's been with CARIS for almost 8 years now, originally providing support and training for process-related products. He is a Hips product manager now. He's responsible for coordinating with clients and other vendors and industry researchers for new ideas and technology, as well as providing outreach and education of the capabilities of the software. He has a Bachelor of Science in Engineering, Geomatics from UNB. And take it away.
Thanks, John. Good afternoon, everybody. Pleasure to be here. I always love coming down to CCOM. It's actually not that far from Fredericton, about 6 hours north, weather permitting. I actually spent 5 hours in Toronto trying to get here. It should have been a 1 hour flight. So good times, but that's the nature of the beast up here on the East Coast. So today I'd like to present something I think some of you have heard about. Two topics actually: variable resolution and some new capabilities we have with autonomous mapping, which seem a little bit disjoint, but I will actually tie them together at the end, so stay tuned. So the big one, focus, there we go. Just to give you some background, I don't want to go through a big sales speech about CARIS, but just to give you an idea of the background we're coming from, I suspect many of you are familiar with who we are anyway. We've been in the GIS software business for about 35 years now, a little over that. We've got installations in well over 85 countries now, about 170 employees across several different continents, the main office in Canada, like I said, just about 6 hours north of here. A decent sized office in the Netherlands and smaller offices in the US, Australia, and the UK. We've been in the business for a long time, particularly in the hydrographic and ocean mapping business, and that's kind of our that's our main industry, and we've been doing it for quite a while. We're also ISO certified, and we're on a bunch of working groups as well, specifically the OGC, ISO, TC211 working group, and S57, S100 with the IHO. So we're on. We've got our hands in many pies. In terms of our product line, one of our lines is the ping to chart workflow. We're the only provider that offers a single one-stop shop to get from raw sonar data out to a nautical chart through a series of software packages. On the processing side, you've got Hips and Sips and on board. That's kind of my domain. Then we have some mid-tier analysis tools with the Bathy database suite that includes base editor, engineering analysis, and law of the sea stuff. And then we have our chart production toolkit with HPD, hydrographic production database, and then S57 and paper chart composer. So that's kind of the background for why we're getting into stuff like a variable resolution technology and why we're pushing the envelope. Of course, spatial fusion. Sorry, I forgot to mention on the web side. So that's our web enabling technology. So the biggest topic I'm here to talk about today is this new variable resolution technology. In fact, it ties in nicely with stuff Brian Calder's been working on with Chart, which I'll actually mention as part of this. But why are we doing it? What's the reason for this? Well, I'll go back a little bit and talk about what do we get with this data. So typically we're using remote sensing data, whether it's sonar, LiDAR, radar interferometry. We have different mechanisms for sensing the ocean floor, kind of on this side anyway. But due to the nature of remote sensing, you're not doing a regular pattern when you're scanning, basically. Depending on the technology you're using, the type of system it is, generally the samples you get back are not regularly spaced. Why is that important? Well, generally we dump this stuff through computers, and they like nice regular data sets. So we try and model these sort of randomly sensed data sets and turn them into some kind of continuous regular model that's easy for computers to understand and work on. So that's the incentive. That's what we're trying to get to. There's various techniques we apply today to get around this problem, because what happens as your density varies, whether it's going from shallow water to deep or from single beam to multi-beam technology, depending on what you're working with. There's different ways to deal with it. So this is an example of a NOAA bag data set, H11749 for those who are interested. So each color range represents an individual bag file. So the red, the green, and the blue are each bag files, 1, 2, and 5 meter resolution. So one of the techniques we use to deal with this varying density is to split it up by depth range. So we say the shallow stuff gets a 1 meter, the mid-tier stuff gets 2 meter, and so on. So we try and divvy that up into fixed resolutions and apply models based on that. But there's problems with that technique. And this is a prime example where at the boundaries between the two data sets, you'll see there's a bit of feathering in the surface. And it's because you're sampling a certain region at 2 meters and 5 meters, for instance, between the green and the blue, and you'll get slightly different depth values depending on what your kind of radius of influence is basically on the grid itself. And so how do you deal with that if you're making products from it? If you're running a contour across that interface, which depth do you pick? I mean, it's problematic trying to deal with that. Of course, ideally you'd stay away from it for contouring. Another option would be using a TIN, triangular irregular network, and which tend to work pretty well, but with the way those get implemented, typically they're in memory only, so it's limited by the computer you're operating on. The TINs can only get so big before you run out of memory, and the whole thing falls over. So they're limited in size. Edge removal is also a problem. Delaunay triangulation, of course, is a standard technique with TINs, but you get that big convex hull around it, and long edges become a problem dealing with those. As well as data holidays, a TIN will tend to just happily mesh right over a holiday, and you won't even know it's there until you look, get right down to the point level and see where those gaps are, which is, of course, important for hydrography, but other applications as well. So what we really want is to be able to define a continuous surface across a large region with varying resolution. We want to, based on our point spacing within each of these areas, we want to manually or automatically adjust the resolution to accommodate, while still giving us sort of a modeled surface, something that's computationally a little easier for a computer to work with. So that brings us to variable resolution. So to explain this, I'm going to start from the basics and identify some sort of foundational characteristics of modeling, and then we'll use that to define variable resolution. So for the current paradigm, we have a single continuous, we have a continuous area of remotely sensed data. We want to define a surface over that area. So we split it up either into raster or irregular nodes at a certain interval. Particularly in the raster case, we have a fixed spacing between points, and then some function that defines how we interpolate values between those grid nodes or TIN nodes. So in both cases, for the raster and TIN, something common would be to do something like a linear interpolation. So if you're running a contour line between two grid nodes, you use a linear interpolation to figure out where that contour falls. So just in point form, we've got with a raster surface, ignoring the TIN for a moment, we have regular spacing. We define the resolution of the spacing ahead of time. That's a priori. We compute a value at every node based on some grading technique, whatever your flavor of choice is. And then we have an understood definition of how to interpolate values across that surface when we're creating products. So that's the raster case. That's today. That's easy enough to understand. So graphically, there's my region. I lay down a grid of some sort at some regular spacing. I compute my node values, and then I define some interpolation between them. So in this case, just a linear one. So I put a mesh effectively between the raster nodes. So that's the raster case. With variable resolution, we actually divide a region up into what we call tiles. The tile scheme can be varying. We'll talk about that more in a second. But for now, we just divide it up into discrete tiles, and each tile gets its own resolution. So instead of one fixed resolution for the entire region, each tile within that region gets its own resolution. And again, the tile patterns can follow different patterns. I'll talk about that more in a sec. But we still lay down those tiles. We define a resolution for each tile individually through some other method, which I'll talk about. Lay down our nodes. Once we have a resolution, compute a value at every position, and then we compute a mesh across it. So that's how we do variable resolution. So in our case, with the methods we've implemented for CARIS variable resolution, we're using a quad tree. So effectively, we start with a bounding box. We split that into 4 pieces, 4 tiles, and then based on some criteria, we keep subdividing it. So each tile gets subdivided based on whatever the criteria might be, and I'll talk about that more in a second. But this is the pattern we're using. So each one of these tiles gets its own resolution calculation. So each one of them can have some distinct resolution from the next. Which is nice for another reason I'll talk about towards the end. So if I zoom right in on the center of this tile into something like this, so here's my computer resolution. I lay down my grid nodes. You can see they're arbitrary spacing. I'm not using, it's not dyadic or anything like that. It's not a multiple of 2 or power of 2. It could be any arbitrary resolution between adjacent tiles. I lay down my nodes inside those tiles and then compute a mesh across them. And that's how we get a variable resolution surface. So we've kind of done a hybrid of almost a tin and a tin and a grid. So we're using the computational efficiency of a gridded surface combined with the flexibility of an irregular network. So it's a best of both approach. Getting into the computation of it. So here's start to finish how we put these things together. So there's some additional complexity now above and beyond a regular raster grid because we're still doing the gridding towards the end of the process, but there's some initial setup time and how you want to determine what those resolutions are going to be. So we start with our input points. And the first thing we want to do is analyze the point cloud or source points and determine what our resolution layout's going to be based on that. For the first release here of the software, we're going to have 2 conceptual methods, 3 functional methods. So the first one will be by depth range. This one maps the closest to that bag example I gave earlier in the current kind of paradigm for how we deal with varying levels of density. So it's simply given a table by the user, so the user lays this out. A lot of HOs already have this in place, which makes it easy. We have a depth range and a resolution associated with that depth range in the table. So from 0 to, a drying height down to 5 meters, it's 25 centimeter, 5 to 10 meters, half meter. This is just kind of an arbitrary example, but you get the idea. So we lay down the tiles, we lay down the quad tree across the data set. The tile splitting, to give an explanation on that, happens so that, well, there's a bunch of things going on, but roughly every tile gets the same number of points, at least within an order of magnitude. So that's how we do the tile splitting. So over deep areas where you have a coarse sample spacing, you get very large tiles. And as you get shoaler, the point spacing gets smaller, the tiles will start breaking down more and more, and you get finer and finer tiles. But that tile, right up at the 5 meter contour is going to have roughly the same number of points as the big tile out in the deeps, like 500 meters. So that's kind of how we break down the tiles. And then we scan across the tiles, and in the depth range case, we produce just a simple statistic on the tile. So min, max, or average depth on the tile, and then the user picks which one they want to map to that resolution table. So we say the minimum depth in that tile, use that to map the resolution I want, or use the average, whichever one you want. And the end result is roughly this picture. So up in the shoaler areas, of course, I've got very fine point spacing. So I get very, very fine resolution tiles coming in there. And then as I get deeper, my point spacing increases. And of course, I get coarser and coarser tiles as you go deep. So I think that's fairly intuitive. That kind of maps a lot to the way things work today. But the beauty of this is you get a single continuous mesh. And you can go right from the 0 meter contour, or even on land, if you've got some topobathy LiDAR. You can go from that down to the abyssal plane with a single gridded product. That's the beauty of this thing with the quad tree and the resolution adjustments kind of as it goes. And the same thing applies to the density techniques. So the density techniques are a bit of a different approach, and I'm going to talk about 2. Somewhat known to ourselves, but somewhat not. Of course, Brian Calder here at CCOM was working on his own variable resolution technique with CART. I'm sure a lot of you in this room are familiar with it. I'll talk about his next because we've implemented his as well. We also developed our own technique that frankly isn't that far off from Brian's. So we've kind of converged on the same idea. In this case, we do the same tile breakdown for our method. Again, the tiles roughly have an equal number of points in them. And then we analyze the point spacing in the tile. And we account for a bunch of things here. And if you like to, I have a slide at the end. I can go into more detail. But we do account for how much of the tile is actually insonified. So if it's at the edge of a data set and there's an empty area where there's no points, that doesn't have any weight on the final resolution calculation. But effectively, we analyze the point spacing. The user defines how many points they want in each node. So they say, I want an average of 5 points per grid node. And based on that criteria, we'll come up with the best resolution for that tile. So instead of the user enforcing some a priori knowledge about what the point spacing is. You just say, make the model whatever the best point spacing I can get out of it. The Brian's method is very similar to our own. The only difference with his implementation is instead of a quad tree, he used fixed size tiles, which is effectively just a subset of the quad tree. So it mapped quite nicely into our own framework. But otherwise, again, he's doing a point density estimation. He's looking at the insonified area within the tile, coming up with the ideal resolution to meet your target, point count per node. So the two methods, they're pretty similar. They'll give you almost exactly the same result given the same data between the two of them. We each have our own little idiosyncrasies. Brian's is better in certain cases, ours is better in another. If you make it up to the Canadian Hydrographic Conference this year, I'll be presenting a paper on that when the time comes. And comparing it with the depth range as well. So the idea here is instead of a subjective enforcement of resolution by the user on a data set, you let the data determine what the best resolution of your model is going to be. Contrasting that with the depth range method, which we kind of put in there as a transition to variable resolution. It's a concept I think everyone's comfortable with. They already operate that way. So it's kind of a stepping stone to get to the density method. So we're not done yet. We're just getting started. So at this point, we've analyzed the point cloud, we've got our tile layout, and we have a resolution map. So I'm going to talk about that more. We store this in what we call a resolution map, and this is actually available as a layer that you can visualize with the data set to see the tile breakdown and see the resolution assigned to every tile. I'll show you that here towards the end. So we've got our layout. We have our map of where our resolution tiles are going to go. So we lay down our nodes, and then we apply our gridding method. So at this point, the nice thing about what we did is that the resolution estimation and the gridding are completely disconnected. There's no dependency between the two. So we can swap out the resolution method, or we can swap out the gridding, and it doesn't matter. You still get whatever product you want at the end. So it's a nice flexible mechanism here. But in terms of computing the nodes, we have kind of the standard options. We have a simple statistic, so a shoal depth or average, or a shoal deep or average. Inverse distance weighting. We have the HIPS gridding methods, of course, as well. The swath angle weighting, which basically takes into account the beam width of the sonar you're using. And of course, cube. Everybody here, I think, is familiar with cube by this point. We also have another interesting option, and frankly, I'm not sure how this is going to get released at this point. With the underlying storage technology we're using, we actually allow for more than one sample per bin. So you could compute a value for that bin, if you like, for that grid node, or you could just keep the original data set. This comes in really handy if all you have is a gridded data set from somebody else. So somebody gives you a bag file and tells you to make a model out of it. Of course, you can't go back to the source data at that point. So you could just bring the bag file into a VR and just keep the original points, if you like. And I'll show you an example of that as well here a little later. But that's kind of an interesting fifth option here. And it has some interesting ideas around that about keeping all the original data. But it's useful again for third-party products, third-party data you're just bringing in. You want to make a continuous mesh out of, so taking all those bag files that NOAA maintains at the different depth ranges and resolution, you can dump all of them in an area into a single VR product and create your derivative products from there. So you can take those 4 or 5 bag files, dump them into one VR, and make one contour set from it, which is nice. At that point, once we have the grid nodes computed, we store them in our Caesar format. So those of you that have used CARIS before would be familiar with Caesar. That's our gridded storage format, gridded and point cloud storage format. We've had around for a number of years now. Very efficient. It uses a chunking and a tiled resolution pyramid. We divide the data set up into distinct squares under the hood. And we create coarser representations of the data as well. So when you first open a data set at an overview scale, you're not loading the entire grid into the display. You're just looking at a coarse, low resolution representation of it. And this lets us do very fast open and pan and zoom kind of thing. Very fast visualization, I should say. So we're using the same technology here now for variable resolution. The technology, of course, supported this quite nicely. So we're still storing the nodes, and we're storing that resolution map as well in the Caesar file. So that's the first part of the equation, and the second part, what it turns out is actually a lot harder, is the display of these things. Because they're variable in nature, you've got to do some cajoling, I'll say, to make computers play nice with them. There's some interesting display things you have to worry about, but we've solved all of that. And so when you display these VR surfaces inside the application, we're actually creating a mesh on the fly on the point data. So the mesh is done on the fly, and visualization as well. So all the computations also happen on top of that mesh. So we're using Delaunay triangulation to display the mesh. You can display it as a mesh network, or we have a nice surface draping engine behind it as well, if you're more comfortable with that view. And the neat thing is it's a seamless transition. So I mentioned Caesar has that pyramid resolution, coarser resolution representation. The neat thing about what they did was it dynamically loads and unloads the points as you zoom in further, and automatically updates the mesh in the background. So from a display perspective, it looks continuous, but in fact, it's actually moving through multiple tiers under the hood. And you're probably wondering about the Delaunay triangulation. I just complained about it a few minutes ago, that we have this long edge problem. Well, what we did was actually kind of nice. The grid nodes that we put across this mesh actually constrain the tin. So that's how we deal with the long edges. So from any point in a bin, it can only cross to an adjacent node. It can't go any further than that. So that's how we deal with the long edge problem from Delaunay. There's a couple other smart things in there that I'm not allowed to talk about. You may notice in this case, I actually have multiple points per bin. This is, for anyone that's been around long enough, that was at Shell Survey 2005, they had the old Plymouth lead line data set. Because this lead line data, of course, it's so sparse, I just dumped the whole data set into VR and didn't do any regridding on it. So I just kept all the original points. And in this case, the mesh just works across all the nodes, and it preserves the islands as well, based on that criteria I mentioned between the grid nodes on the mesh. So that's how we do visualization. So again, we have this mesh display, but we also have a nice continuous surface view on it as well, which you'll see in a second. In terms of production, generating products on this thing, the great thing is it's interchangeable with raster products. So in terms of workflow, when you're generating surfaces, you can use the old single raster, or you can use variable resolution. The tool set's going to work the same on either. The great part about that, and I know particularly it's a pain in NOAA, and I'm sure you folks hear about NOAA all the time around here. In the field, they're maintaining all these different resolution band files when they're processing data. So they're managing 5, 6, 10 grids at a time for every sheet, and every time they load in new data or make a change, they load SBETs or something, they've got to go back and recompute these 10 surfaces. So it's a big pain. Well, now with VR, they can just use a single working product and update just one grid at a time. So it's going to be a lot more efficient in terms of processing capability. And the beauty of this is, you're probably also familiar with directed editing through Cube. The idea is you have a working cube surface that doesn't necessarily have to be your final product. It could be, but it doesn't have to be. So maybe even just for processing, you can use a VR surface. Maybe your deliverable is still a fixed resolution raster. Well, that's fine. You can do all your cleaning with the VR and then produce your final products with a single fixed resolution. We also will be offering some resampling tools as well. Interchange is going to be a big problem on the first release, because we put this out there. Well, there's no standard interchange format for variable resolution. The closest thing we've got is probably ASCII text as a point cloud. There's no BAG format that supports variable resolution, although of course that's coming. But it's not there yet. And even if we get an interchange format like BAG, other vendors have to implement support for it. And I had mentioned that kind of earlier. The hardest part of this was actually the visualization. The storage bit was pretty easy, because we can all figure out regular grids in a database file of some sort. That's not too hard. But visualization and displaying these meshes, it's actually pretty tricky. So we assume it's going to take some time for other vendors to implement this. So there'll be a transition period where we still need to produce these fixed resolution rasters, if you need to give data to somebody else that's working in other software. So we'll have some resampling tools that will let you create a single resolution product out of a VR, or in case, of course, as I mentioned, You can generate them directly in HIPs as well from the source data. Kind of depends on what you've got available. But the option's there. So here's that same bag data set again. So this is a combination of those four. It's actually 4 bag files. There's one just for the deepest water there that I couldn't fit in the screenshot. So that's a single continuous VR grid. So this is the shaded surface display instead of the mesh display. Like I mentioned, we had both options. We've already hooked up contouring to this thing, sounding selection as well. So again, the great part is you're not dealing with 4 or 5 different grids and having to cobble the contours together afterwards after you've generated them under the different data sets. You do it once on a single continuous data set. So again, just making things much more efficient. So I actually took the 4 bag files, and so there's the original display, again color-coded by file. Dumped them all into a single mesh, and in this case I kept the original point, so I didn't regrid it, which is why you get that nice contour following density there, and that's what it looks like in variable resolution. The only hitch with doing this, and it's probably might be hard to see in this scale, right at the boundary I kept all the original points, so you get that bit of feathering between the 2 resolution bands, and that would probably be some manual editing to clean that up, depending on what you want to do. But the beauty of variable resolution is in those overlap areas, typically you have to figure out which point, how do I figure out which node to choose, the 2 meter or the 5 meter? With VR, you don't need to pick, you just keep them both. You just dump them both into the mesh and it just works. Of course, that might be bad. You might have some bad data you've got to get rid of, but generally speaking, you can dump whatever data you want into it. There we go. So that's where we are today. That's what you're going to see in the product coming out. I know I'll get this question, so I'll say it now. August of this year is when HIPS 10.0 is going to go out with variable resolution, and Bathy database will get an update to support it about the same time. So that's when it's coming out. Of course, because we've kind of wrapped this up, we're already thinking ahead to the future and things we can do with this new technology, and that's where folks like you come in. Is coming up with ideas on where we can take this technology. For instance, alternative methods to define the resolution. We have the depth range and the density estimation. I had mentioned the gridding and the resolution estimation were completely separate, and that's the great thing about it. So we can replace the resolution estimation with whatever we want. So if someone comes up with some harebrained scheme for determining the best spacing for a point data set, then let us know and we can try it out. We can plug it in and see what happens. Alternative tiling schemes. We used a quad tree. Brian had used fixed size tiles. I've seen other proposals online for hexagonal tiles, octagons, arbitrary polygons. There's different ways we could do this. The underlying technology, the storage technology we use, supports it. It doesn't care whether it's a fixed size tile or an irregular one. It's quite happy to store that. So there's different ways we could do that. Another interesting idea would be alternative node placements. So instead of doing a fixed resolution within a tile, you could actually do an irregular resolution within a tile. So you could have a tin within a tile if you like. How do you compute and store that? Well, we've got the storage part and the computation. Well, I don't know. There'd be different ways of doing that. Maybe you bin some points until you reach some threshold and then just dump it in wherever the middle point is. Maybe that's an idea. But again, the underlying technology supports things like that. It's not in the software now, but we could do things like that. So that's where it would get interesting. And of course, hybrid data sets where you've got single beam or shallow Bathy LiDAR mixed with high resolution multi-beam. You can do things like that on the right in the upper right there, where you have a sparser data set intermingled with a high resolution grid. The technology supports storing that and visualizing and creating products. The other interesting idea is a resolution map itself as a survey criteria, which is where kind of the autonomous link is going to come in here in a second. So this resolution map is a new product, or it's a new piece of the technology. It's a new concept of storing a map of what you want your resolution to be. So I'm going to switch gears for 1 minute, but again, I'll tie it all back at the end. CARIS on board. Some of you may have heard about it. It was released back in the fall, 1.0 release. At a conceptual level, Well, at a conceptual level, it's effectively a headless HIPS, is what it is. So we have the core technology from CARIS, HIPS, and SIPs, all of our format support, all of our gridding tools, our correction abilities, so sound velocity, tides, all that technology, we took off the interface from it and made it completely headless. And then we wrapped it in an autonomous service that just sits there and sends commands to this HIPS bot, if you will. So that's where the autonomous data processing side comes in. And the main idea of this, it was originally developed for the AV market because those systems need to run autonomously without any human intervention. Turns out that actually there's a lot of applications in manned platforms as well, which I'll talk about a bit in a minute. But we do have some real-time monitoring capability as well. There's a control center just to watch and configure this thing as it's running. But we also have a data service that lets you watch the data products coming out of it in real time as well, if you've got the bandwidth to support it, depending on what your configuration is. So here's a rough diagram of the onboard setup. So at the center of this is the onboard service itself. It runs as a Windows service, starts up when the machine starts up. There is a Linux version in the works, in case you're wondering. I usually get that question too. So the onboard service is kind of the beating heart. This is where all the HIPS logic sits, as well as a file monitoring service. So the file monitor simply sits there and watches a folder, whatever folder you tell it to, and waits for new files to appear. Initially, we thought about integration with SYS or HiPAC or Quincy, things like that, but we'd have to develop a specific interface to talk to each of those. So instead, we simplified it so that it just watches a folder and waits for a file to appear. So you set it to monitor the folder that your acquisition is logging to, and it'll see a new, a .all or an HSX or whatever file. It'll show up, and Onboard will start monitoring it. But it's smart enough to know acquisition's probably writing to it, so it'll sit there and wait, and it'll watch the status on the file size changing, all those kind of indicators, until the acquisition system is finished with it. It's cut the line. As soon as that happens, Onboard will fire up and run through a HIPS workflow of some sort. So the HIPS workflow you define ahead of time, which I'll show you a bit more about here in a second. There's a control center to monitor it, so it's basically just a little web app. You could go to a web address for the machine Onboard is running on, brings up a web page, and from that interface you can see its status, so see what it's working on at the time, start and stop the file monitoring if you like, and a few other tasks. So the Onboard service, by default of course, it's HIPS under the hood. So it will generate a HIPS project as it's processing data, and you can tell it what kind of products you want. So it could be a Surface, could be a Mosaic, could be a GeoTIFF. We support all of that through the surface. So that gets dumped out to the disk. We also have a new program, completely standalone, called the Process Designer. And so I mentioned earlier, you need to define the workflow ahead of time. So basically, you need to tell Onboard what it needs to do to process the data. So what file format is it? Do you want to apply predicted tides? Do you want to compute TPU? Do you want to create a cube surface? You need to lay that out somehow. So this is what the Process Designer looks like. Again, it's a new interface. On the left, we've got all our HIPS processes here that everybody's familiar with if you've used HIPS at all. And you can drag them out to this main area here and start chaining these things together. So in this case, I've got a typical Kongsberg workflow. Convert the Kongsberg data, compute TPU on it, merge it, so that's the georeferencing part. Generate a cube surface from the merged data with TPU. And then there's a new process on the tail end of that called register product. Because this was designed for autonomous platforms, you don't always have a real-time connection. What Onboard supports doing is actually a live feed over a network of the data products it's creating. So you can connect to the Onboard service with any CARIS desktop application and actually see the cube surface getting updated in real time. Of course, you generally can't do that on autonomous systems, particularly AUVs, because you get limited bandwidth, typically acoustic only, between you and the vehicle. There's some overhead associated with providing a live feed of the grid. Extra resources cost extra power on AUVs, and that's a big no-no. So that's why it's an optional step on the end. But if you've got the bandwidth and you've got the power to support it, you can register this thing, and then it'll be available to anyone that wants to connect in and watch the grid update itself in real This is what the dashboard looks like. So this is the control center just in any web browser. Every time a new line appears, that gets registered as a job, basically in the onboard interface. So each one of these represents a line of data that was acquired and run through onboard processing. From the main screen, you basically just get a go, no go kind of status. If there's any kind of failure, this shows up as red. You can go in to figure out what happened. And start and end time, things like that. And you can click on any one of those and get the full, basically what you see in the HIPS output window, you get the full output from the process. So you'd see, conversion start and end, merge start and end, the same outputs you'd see from the desktop. In terms of viewing the data products on the desktop, there's a new menu item now you can go in and connect to. It's effectively like connecting to an internet service. You give it a web address or an IP address, whatever is appropriate to get to that machine. And then the grid comes up with this live display and updates in real time. And the great thing is, it opens just like any other Caesar file would. So you can actually start creating products with this thing as it's acquiring. So you can make contours on this thing as it's generating. And it works pretty slick. The other nice thing is, for a HIPS user, if you're sitting on the same boat that Onboard is running on, because you need the bandwidth for it, you can actually open the HIPS project itself and actually start cleaning the data as it's acquiring real time. About 2 years ago, we had added some multi-user capability to HIPS and SIPS projects with the HIPS file. Some of you may be familiar with that. As far as HIPS is concerned, the desktop environment, Onboard is just another client on the HIPS project. So it works seamlessly. We didn't actually have to change anything to make that work from our end on the desktop. So you can open that HIPS project, and as new lines get converted into the project, they just appear for the user with the desktop open. So they can have that kind of real-time capability. So I mentioned this earlier. This was originally developed for the AUV market as autonomous processing, primarily because the biggest bottleneck right now is the data itself. These vehicles go out, they've got 24, 48-hour endurance, they collect data for that long, they come back to the boat, and you're going to sit there and download the data for an hour or two. Then you got to run it through CARIS to get it processed, and then you know if the mission actually worked. And by that time, you could have transited somewhere else. You don't know if you need to go back, resurvey something. So the great thing about Onboard is that as soon as the vehicle pops up and you get that Wi-Fi link, you could open that gridded surface right away and see if you've got coverage, see if your data's got some quality to it. You get that early feedback, and you can decide right then and there if you need to send the vehicle back into the same spot, or you can move on to the next area. That was the original intention for Onboard, but it turns out, of course, ASVs, by the time we got this thing together, ASVs were kind of coming into their own. You folks have probably heard a lot about the Z-boat. We've done a lot of trials actually now with the Z-boat.
Actually, we've heard about Z-boats.
Z-boats? Oh, is it Z-boats? Sorry, yes. I'm south of the border, so it's Z-boats down here, isn't it? We did actually at Shallow Survey this year. It was a blast. We had some folks from Ocean Science in Baton Rouge, Louisiana, sitting on a canal driving this thing around, and in Plymouth in the UK, we had a bunch of drunk hydrographers sitting around a booth watching a live feed of an Odom MB1 acquiring data with a Z-boat. So that was a lot of fun. So that's kind of the remote capability of these platforms. And then on the man side, a lot of people actually turned out were quite excited about Onboard because it eliminates the monotonous button pushing. So for any of you that have sat on a boat sitting there clicking through HIPS for hours on end, just converting the data as the ship acquires it, it's monotonous, you're bound to make mistakes, and you lose some consistency and of course time doing that, possibly. So the beauty of Onboard is it always does the same process, exactly the same over and over and over again with your data. As long as you get that configuration right, of course, up front. So it can sit there, chew away on the data, and that frees up a hydrographer to just focus on the data cleaning or focus on running a survey, whatever needs to be required. And when that launch returns for the day, whether it gets back to a mothership or it comes back on shore, you've got an 80% processed project, HIPS project ready to go. So you just need to apply your final tides, your SBETs, whatever, and update your surface, and you're done. And that's the beauty of it. It eliminates that lag time between ping and getting a finished data product out. So I want to tie this back in a bit to variable resolution and kind of this pie in the sky idea we've been thinking about a little bit. doing resurvey areas, as an example, or something you know a little bit about the bottom, you could have a situation where you take the ENC, you know approximately what the depth is. If you're doing nautical charting, of course, you know what the density requirement is. So from that, you can actually generate this resolution map. You don't need the source points to do it. You can actually approximate what the resolution needs to be based on the charted depth. So this is completely arbitrary in this case, but you kind of get the idea. You can have some high density areas, some lower density, deeper areas. Whatever the needs of the survey might be, you can lay out this resolution ahead of time. And so our survey mothership shows up on site and deploys some minions, if you will. It deploys some robotic systems, whether it's midwater or very shallow water systems like the Z-boat. That's a system from ASV for deeper water. And these things go out, and typically they're controlled by the mothership. And you know, whether they're semi-autonomous or fully autonomous, they're generally given a specific region, a line pattern to survey. I saw the presentation at Field Procedures Workshop from Damien about doing some autonomous line planning, which is where this gets really exciting. Because what you can do is, this resolution map is your resolution requirement for the survey. So these boats on their own can understand what they need to survey to while they're out there. So they can start filling in these grid nodes effectively as they're speeding along. Computer payload sitting on board just chugging through this data and filling in these grid nodes, and it knows whether it's got them all filled or not. So then you get into some neat things like, well, what if they talk to each other instead? And the survey mothership can just go tie up back at the pub. And these little robots will just float around and collect as much data, stay there as long as they need to, assuming they've got the endurance to do it. They know their operational capabilities between them, especially the stuff I saw Damien do, I know accounts for that. And they can just fill in this survey sheet, and you come back and pick them up when they're done. And I think that's doable with the stuff we've got today. The technology's already there, and that's kind of the cool part. So, how am I doing for time? Close. I can do some questions, or I can show you what this stuff looks like real quick. Any preference? Why don't I just pop up? I'll pop up a VR grid real quick, just to give you an idea of what these things look like. So here is prototype CARIS software. This is a different NOAA data set. The great thing about this, it goes down to about 400 meters water depth across the bottom. This is a data set up in Alaska, H12142. So this is the shaded surface display. You can see kind of as I zoom in, I talked about the mesh getting updated in real time. My computer is having a little trouble running GoToMeeting at the same time. But you get the idea, and I can actually turn on that mesh display if I can manage the cursor. If I switch over, you can actually see the mesh. So the coarser one, so the irregular mesh part here, this is the coarser tile resolution display, and as I zoom in, it's loading in the finer and finer data sets as I get in. So I get up into the shallow areas here, and we can start to get into the actual full resolution grid. And then as I go deeper, in this case, you can see the tiles get coarser and coarser as I go. So here's that resolution map, represented as an additional layer. So I can turn that on as I zoom out. So anything shaded blue is not the full resolution, and as I zoom in, once it gets down to the actual tile, it'll turn orange. So that's what the difference is here. And this is effectively kind of a vector layer, so you can actually query these tiles as well. So I can see this particular tile is a 7.5 meter resolution. In this case, it was a CARIS density estimation. Again, Brian's method would probably give you exactly the same answer because they're both pretty similar. But you can go in, you can query these. I can actually visualize the grid nodes as well. I turn that on. So there you can see the actual resolution represented graphically as well. And you can see again the deeper stuff. As we would expect, again, there's no a priori assumption about resolution, but because it's surface multi-beam, as you go deeper, points get sparser and the resolution adjusts itself accordingly. And that's variable resolution. So any questions?
Can you look at that in 3D?
Yep. My computer may have trouble with this in GoToMeeting. Fair warning. So that's the 3D. So that's just the surface shade. This is a prototype, so the display is a little finicky. I'm going to have to do this twice. Do that. I get back to there's the mesh. I can hear my computer spinning up. So you can see as you get closer, it starts loading in those finer resolutions until you get down to the full mesh. So if you get over, running it from here is a bit tricky. So you can see where the tiles fall down across the data set, and again each one does a certain level of density based on the point spacing internally. So if I do this, set that right down on there, you can kind of see how it goes from dense, or very dense grid down to coarser.
For those data sets where data has already been collected and you want to then determine the optimal grid resolution, can you discuss how you determine data density? The approach
Yes.
taken to determine data density?
I can give you the exact algorithm if you like. If I go here. So again, this is our method, and Brian's method is very similar. I could talk about that as well. So I already talked the quad tree is part of this. So we lay the quad tree down. We split it geographically initially, but it'll go down until they all the tiles have roughly the same number of points in it. And then for each tile, we create a super fine grid, and we're talking like 0.00001. And then we bin the points into it. We dump the points into that fine grid, and then we start partitioning that and counting how many soundings we're getting, and then we basically just collapse that until we get to the point where we meet the density criteria the user gave us. So at 5 points per node or whatever. And then we return that value as the final resolution for the tile. And there is an extra anti-clustering scan that happens at every iteration as well. Basically what that's looking for, if you happen to turn on one spot and you get a whole whack of points in one specific XY location, that can tend to throw off the density estimation. So we actually normalize the point count a bit as an anti-clustering technique to get around that, and actually works pretty well. That high density points in one spot won't blow your resolution out. Works pretty well. Brian's method, I don't know if he made it in the end. I don't see him at the back. I'm generalizing a whole bunch of math that Brian does here, but generally Brian's looking at, for each tile, the effective covered area based on beam footprint or a circular assumption. There's a couple of different techniques we're playing with right now. And based on that insonified area in the tile and a target density, that's how he figures out what resolution to use to get that point density. So it's pretty similar. We're both using area-based techniques and trying to get to a target point density. The math and approach is a little bit different. Interestingly enough, during the implementation here, Brian's method is much more efficient on HIPS data. Our method's much more efficient on the general point bucket data because ours isn't optimized for time sequence linear data, Brian's is. So little things like that. It's only a difference of about 10%, but little things like that. So the idea is we're going to release both of these techniques, let the user decide what one's more appropriate. So that's the two density ones. Yes, Lindsay.
Yeah, thanks for that. You've sort of established a great flow, and it looks much more modular now.
Yep.
And there's lots to do with the density estimator, and I would see people either here or other places wanting to do with it. And I like your model builder or design you have. Are you going to open it up with an API for people to be able to then say, oh, I want to try this and I want to do that? It seems like you've got a good base and it could add a lot.
That is the plan. Actually, for this release, you'll have command line access to run them, but you'll still be stuck with our version of it. So once we get the sort of command line and API side hooked up, then we'll start exposing, okay, do your own math. That's kind of the next step after we get this API. We actually just spent the last 8 months or so trying to finalize a public API. And we've been doing that, we're still finalizing it, to be honest, for the HIPS 10 release. But that is the plan. And certainly if in the interim, after this thing goes out, if specifically anyone here has some ideas, I'd be quite happy to hear from you and discuss it. Any other questions?
Still got about 5 more minutes. Any more questions? Nope. Thank you.
Thanks.